of x and y. Okay, it's simpler. Suppose that I ask you to plot a function that is, and I call theta this angle. Okay. Now, suppose that I have some function, okay, which is a function of r and theta, and this function, so r and theta are now distant from the origin and theta, and this function is simply equal to the cosine theta. Okay. Then I ask you plot it. You might say, what do I plot? I might try to plot versus theta, but then it's a trivial plot, the cosine. Now I want something that tells me for every point what is the value of the function, right? So you might think, okay, let me add a third axis. So if this is x, this is y, sorry, I have z, and I plot my f of theta there. But this is also not very particularly nice to see. Okay? I have a further possibility. Let me plot the function by showing a stick, a little piece of stick, which is this length. Okay? So for theta equals 0, the length is 1. Okay? For theta equal to 45 degrees, the length is square root of 2 over 2, 0.7, something here. Okay, for theta equal to, say, 60, something, it's 1/2, right? For theta equal to 30, it is square root of 3 over 2, so 0.85, something. Okay. So I join these points. Okay, sorry, perhaps it's not particularly faithful. For theta equal to pi over 2 is 0, so I'll do that. I'll draw it here. Now, it's not beautiful because first of all, I didn't plot on scale. But for theta negative is absolutely the same. Okay, so something like this. And here it would be same shape, simply negative. If this is positive stick, this is a negative stick. Okay, this is the plot. That's it. A stick proportional to the value of the function. Okay, then if you have a third axis and the function is symmetric around the axis, it's simple. The stick is the same, whatever angle you have there. Okay, this is, for instance, the way you plot the PZ orbital. Okay, the z, that's the y. You plot it this way, and it's symmetric around z because p doesn't. And here I'm defining theta starting from the z-axis, not from the x. Okay, so it depends on what you do. Is it clear?
Yes. So in the case that we have this spherical harmonics for 2, 0.
The states.
Yes, the d state. And we know that, okay, apart from just thinking about the normalization constant, it's dependent on cosine, but 2 cosine squared minus 1.
Yeah.
Yeah. So I was thinking that the plot would just be symmetric, and that's probably.
Let's see. Yes, you're curious about the d state. Let me see how they are plotted in the function here. Which of this?
Yes.
This one, 3 cos square minus 1, which I think is this.
Yeah. So I was expecting it to just be straight, but then this is.
Yeah. Okay. Let's look. So the idea is this is a small exercising session. Okay. So the idea is try to plot 3 cos square theta minus 1, which is the proportional to the y0 spherical harmonics. Okay. Good. So let's try to do it. I will do it in the. It's enough. Okay, if I do it, for instance, this is the y. Okay, don't worry for the x. Will be symmetric around the z-axis. Okay, so let's see. Theta is equal to 0 there. Okay, so the value of this function is 1, 3 times 1, 2 minus 1, 2. Okay, so let's try to be now more faithful. So if this is 1, this is 2. Okay, so there it is. Then where is this object equal to 0? When the cos square of theta is equal to 1/3. So cos theta equal to 1 over root 3. Okay, there is some magic angle for which this object goes to 0. Okay, suppose that I have it something like this. Good. Before that, it will be something of this kind, right? I don't know how to plot it carefully, but it will be something like this. Okay, at theta 0 you get 0. Now suppose that you go beyond theta 0. For instance, let's go to pi over 2. This is 1, and this is, sorry, this is 0, and this is minus 1. So there is here a stick of length 1, but with a minus sign. Remember that these balloons are charge distribution, it will be positive or negative. So it's kind of, think of as charge distribution. It's really the amplitude. Okay, so the modulus square is the probability of finding the thing. So this is minus 1. So between theta 0 and pi over 2, there will be some other balloon like this. Okay. And here you do something like this. And here you do something like this. And then you can repeat. So here you have, here, by the way, theta and pi minus theta, the cos square is the same. So if the sign is positive here, it will be positive there. While in here, I think this little belt is like one of those things that you use to swim. Okay. Okay, so it's something like this. All right. Yeah. And this angle that you see there is this theta 0 equal to 1 over. This is it. Okay. Good. So let's stop. Okay. And we do today a very important subject. Okay, so today we will talk about measurements. Okay. Measurements in quantum mechanics. I will just present very sketchily the orthodox von Neumann way of thinking about measurements. Our guiding principle would be a certain Gerlach experiment where you measure the speed. Okay. But before I talk about measurement, let me just recall a few other things. First of all, remember that observables, okay, are connected to Hermitian operators. Okay, we said this already. If you want, it's one of the postulates of quantum mechanics. Now, every Hermitian operator has a spectrum, right? And you know that the spectrum is the eigenvalues, okay? Eigenvalues. And you know that the set of all the eigenvalues is a real, each eigenvalue is real, right? It could be discrete, it could be continuous, it could be partly discrete and partly continuous, okay? So that's the spectrum. For notational reasons, I will think of a discrete spectrum so that I can write sums. Okay, but in general, you could think of a mixed thing. So suppose you also know that there is a theorem that tells you that every admission operator in the Hilbert space, okay, this operator are in the Hilbert space of the problem, can be somehow diagonalized in the sense that you can find, so to the admission operator, let's call A the observable, A hat the corresponding admission operator. This object has a set of states, okay, which are eigenstates of the operators. Let me specify the notation. I call A, little a, real, the eigenvalue, okay? This is the eigenvalue of the one of the eigenvalues of the operator A. Now this extra index J, okay, denotes a set of other quantum numbers that somehow do not play a role in A, in the sense that all these J's are degenerate, okay, eigenvectors. So the eigenvectors do not necessarily have to be only one. There could be many. So I will specify J equal from 1 to some degeneracy of the eigenvalue A. J could be 2, 3, infinity, whatever. Okay, this is a number of degenerate states with the same eigenvalue A. I know that different eigenvectors can be always chosen to be orthonormal. In other words, I assume that if I have phi A prime, J prime, scalar product with phi A, J, that is automatically 0 if A is different from A prime. Remember that eigenvectors associated to different eigenvalues, we prove this very simple proof, are automatically 0. If they are A and A prime are the same, then I can always choose all the J's to be orthonormal to each other. Okay, so there is in general another object there. Okay, good. So this we know. Now, how do I construct the subspace in which the subspace of states which have eigenvalue A? I do the following. I define the projector on the subspace with eigenvalue A to be essentially phi A, phi A. Now, if there was only one, this would be enough. But in general, I have an extra index J, right? And I have to sum over J from 1 to G. Is it clear that this is a projector in the subspace with eigenvalue A? Okay? Good. Now, since the different eigenvalues are orthogonal, these projectors are such that if I do PA, A prime, then certainly if A is different from A prime, I get 0, right? Because I get the scalar product of an eigenvalue A and an eigenvalue A prime. But if the two are the same, these are projectors, okay? And therefore, you know that pi squared is equal to A, okay? A system of projector of this kind is called an orthogonal system of projectors, okay? They come out automatically from any emission operator, any observable in the Hilbert space. Okay? Now, there is a very compact way of writing the operator in terms of the projector. Let me just tell you. The operator is the sum over the eigenvalues, the eigenvalue times the projector over A. Okay? So simply in each subspace, okay, think of diagonalizing the operator. In each subspace, it is just A in the diagonal. Then you change the subspace, another A. Okay? And this way of writing the operator is very useful. But first of all, the identity, you remember completeness, right? the identity would be sum over A. And if there was only one, I would write this. But now we have to remember that there are many, okay? So let me just write the corresponding generalization. It is this. Okay, and you realize that this object here is pi A. So what I'm writing here is that it is a sum over all eigenvalues of the pi A, okay, of the projectors on eigenvalue. Okay, good. Now, take a state. Take a state. Obviously, I can write the state as identity times the state, right? And now I express the identity in terms of the projectors A, and I write this as sum over A of projector A sum. So I write every state, okay, as a sum of projectors on the axis. The axes are the orthogonal system of projectors P pi A. Okay, so it's pretty much like when I take a vector and I write the components on the x, on the y, and the z. Okay, I'm doing that. Now, let me just do one little step. These states are generally not of unit norm. If this was of unit norm, the individual projections would be smaller, right? Good. So let me just express the thing in terms of the state, the projection, sorry, divided by its norm, okay, times the norm. I'm just doing nothing. I multiply and divide it by the norm, okay? So this object here now is a projected, is a component along the A axis, but of unit norm. And this is the length of the projection, which I keep track separate. Okay. So I'll give names to this thing. So this object will be my psi A, which is the original psi projected along the A eigenvalue, but with unit norm. Okay. This is a coefficient, CA. Okay, so I've rewritten my state, okay, in terms of sum over all eigenvalues, CA, psi A, where these are projected along each eigenvalue, but with unit norm. Okay, very good. All this is extremely simple, right? But now I want to point out to you several different ways of writing this coefficient CA. First of all, this CA evidently is equal to what? It's the usual way. This is an orthonormal component, okay? So if I take psi and I take the scalar product with psi A, I get CA. Right? So one way of writing CA is also equal to this, right? Yeah. Good. The other way we just learned is this. I mean, the first way is the definition, the norm of the projection. The second is the scalar product. Let's calculate CA modulo squared, because it will be an extremely important one. Okay, it is equal to the modulo square of this object. Okay, I can write it in several ways. For instance, I can write it also as this, so the modulo square of so the length square of pi A psi. Is it clear? Okay, but this is equal to psi pi A, psi, right? I just write the vector times this bra, okay? That's it. But pi square is equal to pi. So this is also equal to psi pi over pi. Okay, very good. Now, let me give a name to this object. P of A will be the probability in a while. I will tell you that this is the probability that in a measurement of the observable A, I get the eigenvalue A. More in a second. Don't try to memorize. Okay? So this modulus square of this projection of the state psi is this PA. Okay? And it has also this very nice appealing form. So you calculate the expectation value of the projector on the state psi. Excellent. Now, one nice aspect which suggests that this might be a probability is that indeed the sum over A of this CA modulus square, okay, which is the sum of the square projections of the vector. The vector has unit norm. You can show very easily that this is equal to 1. Okay? So in some sense, if I define this object to be the probability, this probability is correctly normalized to 1. You can also look at this object to show that it's really 1. Look at this expression. It's the sum over A psi pi A psi, right? According to my definition, the probability is the expectation value of the projector. But the sum over A of the projector is the identity. Okay? So you realize that this is nothing but psi, which by definition is 1. So we have indeed verified that the sum of this square coefficient is 1. Okay? So all this is a bit formal, but it's important to keep in mind. Okay, it's in the first half, 1.5 page of the chapter 7 of the note. Please try to make sure you understand. Okay, now comes the measurement part. Okay, so this is in some sense a postulate now. Let me just abbreviate the story so far. I will write. We'll just condense my story here. Sum over A of CA side A. And also I will erase some of the things. Don't worry, it's in the notes, but I will write now for you the fact that CA modulus square is equal to PA is equal to psi pi A psi. Okay. So the probability PA. Okay, now let's yeah.
So this the measurement that we started with looking at the projections of orthogonal states. If I think about this form of spin, and we have this sort of a pure state that we sort of think of projections of just.
I think you are anticipating things that will come very, very soon. Can you just take the question suspended for, say, a little bit? And after I do a few other things, then you do the question if it is still not clear. Okay? So, the postulate is the following. If I measure the observable A on psi, which means that I have prepared, that's a very important thing, I have prepared an ensemble, okay, of systems all in the state psi, okay, and I keep doing my measurement. I prepare psi, I measure, throw it away. I prepare psi, I measure, throw it away. Okay, this is the idea of measuring the observable on an ensemble of identically prepared systems. Okay, now in each measurement. So, okay, so if I send the state psi to the measuring apparatus. Okay, the measurement produces one of the eigenvalues A. Okay, I do not measure averages or whatever. Okay, for instance, if I measure the spin, I can measure +1/10 or -1/10. Okay. There is a probabilistic nature of the outcome. Okay, the outcome is any of the eigenfunctions, any of the eigenvalues, and if I collect the statistics of this measurement, I will see that the probability that I measure the eigenvalue A is PA, okay, some value PA. So according to the theory, I will be able to not only to measure, I can always measure things, but I can predict, okay, what is this probability, okay? And the theory tells me that the probability of measuring in a measurement of the observable A, the eigenvalue A, given the fact that I prepare the state psi, is it this notation clear? It's like when you do conditional probabilities. Okay, so I have prepared my state psi. Okay, and I want to know what is the probability that I measure the eigenvalue A. Then the theory, quantum mechanics, the postulate, fundamental postulate, tells me that this object is precisely equal to the psi A psi. Okay, which is also equal, according to the manipulation we did a while ago, to the projection square of the state psi on the eigenstate psi A, on the projection around A. Now, we have already proved that the sum over A of pi A is 1, so this is a consistent definition of a probability. Okay? And in some sense, it generalizes. If you remember, so if this is equal to psi A psi modulo square, it nicely generalizes this probability density psi of x, okay, which we discussed at the beginning. Remember that was psi, the wave function modulo square. But now we learned that the wave function is the projection on the eigenstates of the position of the state modulo square. You realize the very strong similarity between the two things. Okay. Now, if I have the position, then that's the wave function modulo square. If I have any other eigenvalue that I'm measuring, any other, sorry, observable, any other operator, then I have to be equipped with the components along the eigenvalue A, and the modulo square of the state of those components will give me the probability that I find the eigenvalue A in the measurement. Okay. There is a second part of the postulate. So this is somehow the von Neumann postulate. Okay. The second part is what happens after the measurement. Okay, I measure and the state and the system exits from the apparatus, and if the measurement is somehow non-destructive, okay, so if I still have a system, because sometimes measurements are destructive, I just hit the screen and that's it. Okay, but suppose that I can create a hole in the screen and the system passes, like in this spin thing, then I know for sure that the resulting state will be psi A. So the system, remember that the system was in a superposition of all state psi A, and after coming out of the apparatus and measuring A, okay, I get the state in one of the projections. This second part is called collapse of the state. Okay, so the state before entering the apparatus was a sum of many eigenvalue projection with certain coefficients. After, it's only one, the one that I measure. I repeat the experiment, I could measure a different A prime, okay? So I'm not sure of which is the final object that I get, because, I mean, I get possibly a different eigenvalue, and I can accumulate statistics of the eigenvalue. Is it clear? Okay? So as you see, there is an element of uncertainty here, an element of probability, which is somehow new and strange, because so far we have discussed about Schrödinger equation, diagonalizing things, or the evolution in time. Everything was perfectly mathematically, I mean, deterministic and no surprise. But when I measure, okay, I have some apparatus, so my system interacts with this more or less classical apparatus. I do something, okay, and at the end I can measure one of the eigenvalues with a certain probability. One or another, okay, all of them obviously can come out. And again, you can think of this as you send states to a Stern-Gerlach, okay, and the atoms either go in one spot or in the other spot, okay. So I know that I'm measuring the spin along, say, Z or along N, okay, and the eigenvalues are +1/2 or -1/2, okay. At the end, so if I put a hole at the end, the state exiting from the system is a spin along the direction that I have measured. Okay, so even if I started from a spin which was mixed. Okay, now before so before proceeding, maybe I can make this useful. Well, not now. So let me stress once more this aspect of the story. And then we do a few examples. So, so I have a measurement apparatus. I send in the psi. I get out a psi prime. It's a change state, which is equal to this psi A, which, as I told you, is the projection of the state on a certain eigenvalue divided by the modulus so that it is normalized. Okay. Now, suppose that I now measure A again. Okay, so after having done this first measurement, immediately after, I send this state to another very, very similar machine. Okay, so it's a machine that measures again the operator A. The same. So if this was sigma Z, the spin along Z, I measure along Z again. Don't be confused and thinking that measuring the spin in any direction is the same measurement. No, if I change the direction, it's a different operator that I measure. Okay? Suppose that you do measure the same operator. Okay? Then question, what eigenvalue would I obtain? Suppose that in the first measurement I got A, say +1/2 of the spin. What eigenvalue should I obtain in the second measurement? A for sure, the same, okay? Because, I mean, there is no longer a superposition of different components in the state. It's only a state along A. So if I measure, I must get, so the thing is that I measure A again with probability 1 this time, okay? This is a very important thing. So if I do two repeated measurements, the first one somehow filters one of the eigenvalues, A. The second one confirms that the, eigenvalue A should be the outcome with probability 1. Okay? It's like trying to measure the spin along Z after you know that the eigenstate is an eigenstate of spin along Z. Okay? You will go through the hole that you have made into the apparatus. Okay? So it's like I got the first polarizer analogy with light. You have photons, so light, okay? You put a polarizer screen. After the polarizer screen, all the photons are, say, polarized vertically, okay? I measure again with another polarizer along the vertical, and the photon passes for sure. Some of the photons here, which were not polarized along Z, didn't pass, okay? But the ones that passed will pass for sure also the second screen. If I rotate the screen, okay, then chances are that the photons which are polarized along Z wouldn't pass. For instance, they could pass with some probability. Okay, so they must be the same. Now, there is another aspect of the story. Suppose that I measure another operator, B. But the operator B is such that A commutator B is 0. Then the observable B is said to be compatible. Okay? So the observable B is compatible with A if they commute. What is the nice thing about commuting? They can share the same eigenvectors, okay? And in particular, you remember in the proof, the crucial idea is that if I have a certain eigenvector of A with eigenvalue A, and I apply B, I do not go out of that little subspace of eigenvalue A. You remember? Okay, good. This means that B does not disrupt somehow A. A keeps being A. So what is the answer now? Well, I will get one of the eigenvalue B, obviously, which I can get. Remember the picture that we drew. This was all the eigenvalues A, okay? Diagonalize. Now I try to diagonalize B in this subspace. I will find some B1 and B, say, GA. Okay? One of the eigenvalues of B in that subspace, this will be the value that I get in the measurement. And finally, I will, for instance, get the state that comes out, psi of B. Good. The probability is obviously calculated with the same formulas. The nice thing about compatible observables is that if I measure A again, okay, then I know that I will obtain A, the original one, for sure, again with probability 1. Okay, so somehow the intermediate measurement of B, if B was compatible with A, does not disrupt the measurement that I did in the first place. So if I remeasure A, I will obtain the same eigenvalue. Okay? So this is all I wanted to tell you about this measurement story. Now let's do a few exercises. Yeah.
What's the probability when you measure B?
You should apply the same rules. So I do have now a state. So, here the state is psi A, okay? So the probability of measuring the observable B, okay? Of measuring some of its eigenvalue, one of its eigenvalue B on the state psi A, okay, is equal to this formula, okay? So psi A times the projector on the eigenvalue B, okay, times psi A. obviously, these are projected already. So here you do have. Here you do have. Okay, let's do the algebra. Here I have psi pi a divided by psi pi a psi, right? Remember that this object here, psi a, was, where did I write? This divided by this. Okay, so I'm putting it here on the left, I put it on the right. Okay, here, and here I have pi b in the middle. So this is the probability that I'm looking for. But now remember that this is equal to the square of pi a. And these two things commute. Okay, the projectors on eigenvalues of two commuting operators are commuting objects. Okay, so if I do that, what I get is essentially equal to psi, the projector on A, the projector on B, divided psi, divided by psi pi A. Okay, so you can calculate. It's a similar formula to the previous one. Okay, let's do some. Well, before I do the exercise, let me just do some formal manipulations, which are useful. Suppose if you do several times this measurement, okay, in the lab, you keep, yeah. Oh, we're just exercising. Okay, you keep track of all the eigenvalue A, and you do histograms with certain probabilities, right? Okay, this is the pi A, and this is the eigenvalue A. You just in the lab collect experiments, right? And you measure repeatedly on the same state side. And I ask you now, what is the average value, the average that you measure for the observable A? Okay, then you would answer, without knowing quantum mechanics, it's simply the sum over A of the outcome I get as the probability of getting A. But now, this is equal to the sum over A of A times, remember that the probability was psi, the projector on A, psi. But now you realize that this is equal to the so-called spectral decomposition of the operator A. Okay, so this is equal to psi A psi. So the expectation value, in the sense of a bracket that we have invoked several times, is a real quantity, remember, is nothing but what you expect from a measurement in this scheme repeatedly for the average. Okay? Is it clear? And obviously, in the same spirit, you can calculate the square average, okay, in order to calculate the standard deviation in the measurement, right? So you can calculate with a similar spirit the average. Let me just erase a little bit here. If I want the spread in the measurements here, I want to associate some error. What I should calculate is somehow A squared, which is the sum over A of A squared times the probability. And with that, obviously, it's easy to, and you can prove very easily that this equals psi A squared psi, okay? And therefore, you can easily define the standard deviation, delta A, to be the square root of the average of the squares minus the square of the average, okay? And you can immediately write the expression in terms of essentially the square root of psi A minus the average of A squared. Okay, so it's a bit long, but it's a very simple expression in terms of expectation value. Now, there is a generalization of the Eisenberg principle that you can prove, okay, which is given here as an exercise. You should try to show that the uncertainty in the measurement of A times the uncertainty in the measurement of some other observable B is greater or equal to 1/2 the modulus of the expectation of psi of the commutator of the two operators. Okay? In other words, if the two operators are compatible, so they commute, in general, I can reduce their uncertainty to 0. There is no lower limit because the commutator is 0. Okay? And therefore, I can, in principle, measure them simultaneously with infinite precision. I'll show you with an example how to do that. If the two operators do not commute, like x and p, here the commutator will be I h bar. And you see that the modulus of this object is just h bar. Okay, so h bar over 2. Now, how you reduce the uncertainty? How do you prepare states which have arbitrarily small uncertainty in two commuting operators? It's simple, right? I take a state. Okay, the state is not a state with uncertainty equal to 0 in both, but I filter first of all with the measurement of A. Okay, so I get a state psi prime, which is psi A. Now I filter with a compatible observable B, and I get some other eigenvalue for B, which is I call B. So the state that I get here is a state which, if I measure A on it, I get A, and if I measure B on it, I get B repeatedly. Okay, so I have prepared states. Okay, by just filtering two commuting observables, which I know that if I measure A, I get a definite eigenvalue, and if I measure B, I get another definite eigenvalue. Okay, so the uncertainty in both measurements is 0. Right? Okay. So don't think that any state, obviously, will be good for both. But I can do filtering processes which prepare state with 0 uncertainty in the two observables. Okay? For x and p, I will be able to do it. If I measure the position, okay, I know that something is here, the momentum is completely scrambled. And if I measure the momentum, then I essentially scramble the position. Is it clear? Good. Let's do a little bit of practice with Stern-Gerlach, and then maybe the question that you were posing, it's relevant. Okay. So I have a Stern-Gerlach machine, which you remember is made of essentially, if I send states in the machine, there are two holes, okay, which I can block selectively, and I know that inside there are magnets, okay. I draw the profile. This is the north, this is the south pole, okay, and I know that the spin will go here or there. I can block one of the two. Okay. Now I know that, for instance, if I block this object, this Stern-Gerlach say along the z-axis, okay, will produce at the outcome here a state that is the plus 1/2 along the direction z. Okay, so what I'm doing, I am measuring the spin along z. Okay, and in this case, I am filtering. Okay, so the outcome might be essentially this or that, so plus 1/2 or minus 1/2. But if I block this, I'm sure that I am collapsing my state into this state with eigenvalue plus 1/2. Okay? If I change my blocking, and I put here the blocking here, I get this. Okay? So each state that comes in the system will produce at the outcome a corresponding eigenstate of SZ. Okay? Notice that in this standard apparatus in which I send the thing from an oven, this is far from being a state. You will learn these are density metrics that describe the system. But suppose that I have already done some filtering. So for instance, I have already produced my system through a Stirling-Gerlach, okay? For instance, along Z. Okay, so what I send here is already the object coming out of the plus state along Z. Okay, then what happens here? Second measurement of the same operator. All atoms will go here. Nobody would go here. Okay, because they are polarized out. Okay, I will confirm with probability 1, I get that the spin is there. Good. Okay, this trick can be used for state preparation. Okay, so by just blocking things, you are sure that you are preparing spin in a given direction. And you can also play the trick of rotating the apparatus. Okay, so if I rotate my apparatus in the direction, say, n in spin space, I know that if I leave this hole open, I get the plus 1/2 in the direction n. Okay, if I leave this thing open, I will get minus 1/2 in the same direction. Okay, very good. So now let's play a little bit. I ask you, suppose that I prepare some state. Okay. So I prepare a state psi. I don't know what it is. Okay, it's a state, spin state, but I don't know exactly which state it is. I send it to a Stirling-Gerlach filter in the direction n. I will denote in the following way: Stirling-Gerlach n. So there are two holes, and I want to know the probability that the outcome is there. So I get plus 1/2, and the probability that I get the outcome there, minus 1/2. Okay. According to the postulate we just saw, the probability that I measure, say, the state plus 1/2 with the filter apparatus n, okay, in the state psi. The notation is a little bit, I mean, not precisely the same, but you understand what I mean. Okay, it's equal to psi. Let's look at this expression. Is the projector on the state plus n. Okay. Remember this projector on the state plus along n. We commented the last time that the phase ambiguity on the state disappears. Okay, and in fact, this object, we saw it last time, can be written very nicely in the following way. These are Pauli matrices divided by 2. Okay, so there it is, our calculation. The calculation is that this is equal to, well, it is this. Okay, so suppose that the state that I send there is now, so psi is equal to a state plus along Z. Okay? So the experiment is I do some Stern-Gerlach and I prepare states with spin along Z. And I send him to a second filter with the Stern-Gerlach along N. And I want to know what is the probability that my first spin along Z passes through the apparatus. Okay? Then this object, I should just calculate here the plus Z. And therefore, what I have is equal to plus Z, the 1 plus N dot sigma Pauli matrices divided by 2, the plus Z. Is it clear so far? Okay. Now, the Pauli matrices and this state along Z have a simple relationship, right? The only object that survives, okay, remember that this is a sigma Z, which has a plus and a minus 1, and then there are sigma X and sigma Y, which are off diagonal, right? So what do you think that would survive of the three components that appear here in this expectation value? Huh? The sigma Z only, okay? So you can actually rewrite this object as cos theta times sigma Z. Okay? But the eigenvalue here is plus, okay? So the answer is 1 plus cos theta divided by 2. Okay? And believe it or not, this is equal to cos square of theta over 2. Okay? Remember, theta is the direction in which I have aligned the second apparatus with respect to Z. Okay? Good. So the probability that I get the spin passing is cos square of theta over 2. I mean, it's no longer 1/2. So far, we usually have probabilities 1/2 and 1/2, but now you can test this. Okay, you just repeat several times the experiment with different theta, and you see if it is cos square of sine theta. Obviously, if you do this, the other spin, okay, the probability that the other spin passes, you have to repeat the same thing, but now you have to put minus here. And needless to say, you have 1 minus theta, okay? And you can verify that the answer this time is sine squared of theta over 2. Okay? So let's do an example. Suppose that the second spin is along X. Okay? So you put the filter along X, which means that theta is equal to pi over 2. Okay? So the probability that you send now a spin along Z and it passes the say the plus 1/2, okay, along X is equal to cos square of pi over 4. 1 over root 2. So 1/2. Sorry, the square is 1/2. Okay? So if you do this calculation with theta equal to pi over 2, what you get is that this probability is 1/2. And the probability that if you send the spin down, it passes again from the same filter. The filter is this open and this block. Okay? Still 1/2. Very, very intriguing. You have a filter that selects the spins along X, okay? More precisely along plus in the X direction. You send a spin along Z, and you would say that it shouldn't pass it, right? It's along Z. Our classical intuition says that they have nothing to do with each other. Not so, okay? You can expand the state along X into an eigenstate of sigma Z, and the answer is that the probability that this object passes is 1/2, and if you send a down spin, still same probability, 1/2 that it passes, okay? So careful to the classical intuition of the spin measure. obviously, I can actually change a little bit the thing, and I could, for instance, do reverse. So I prepare now states psi, which are eigenstate of say +1/2 along n with the first filter, and then I measure the spin along z now. Okay, so the second filter is in fact along z. Okay, and I can ask you what is the probability that with the second filter here, for instance, I measure +1/2 along z. Okay, given that the state was the +1/2 n. Okay, the answer is that I should take the expectation value on the state that I have prepared, the psi, which is +n, okay, of the projector along z. Okay, the projector along z is what? Okay, it's simply the state plus z plus z, right? So the answer is the modulus square of +n plus z, okay? Which you realize is totally identical to the object that I have there, in the sense that here, this object is written explicitly is plus z plus n plus n plus z. Okay, it's the modulus square of the same object. I simply have exchanged the two objects. Okay, so in some sense, the probability of measuring plus z by preparing plus n is exactly equal to the reverse probability of measuring plus n by sending in the plus z. Okay, and it's still cos square. So practice a little bit with this objects, so that it's sure that you know how to calculate things, and in particular. Okay. So let's okay, now we play this game. So I prepare with a filter the state plus n, and I measure repeatedly sigma z. Okay, remember I could get this or that, this with a certain probability, and this with another probability. Okay, remember that the probability of getting this is cos square of theta over 2, and the probability of getting this is sine square of theta over 2. Okay, now I ask you, what is the average of the measurement? Okay, so I measure +1/2 with this probability and -1/2 with this probability. Okay, so the average plus n of sigma z measured on the state prepared to be plus n is equal to 1/2 times the cos square of theta over 2 minus 1/2 times the sine square of theta over 2. Okay? Now, you know how much is this? This is 1/2 times the cos square minus sine square of theta over 2, which is trigonometry, the cos theta. Okay? So 1/2 cos theta. Okay. Now you can verify the following striking thing. If I do the same construction and I try to calculate plus 1/2 n, and I measure with a Stern filter along x rather than z, okay? I do my measurements, probabilities of going plus and minus. So what you get is the following: is 1/2 the sine theta, the cosine theta. Okay, and if you measure similarly, so these are exercises I ask you to do. Okay, so the probability of measuring the y, the expected value of the y, is equal to 1/2 sine theta sine theta. Okay, so why each individual measurement is very strange. For instance, I can measure a spin along x being either plus or minus, although the spin was along z, and I would say no, the spin is not along x. Okay, but I don't measure 0. If I measure the spin along x, I would measure either +1 or -1. So I don't measure the average. The average might be 0 because half go plus and half go minus. Okay, so the average, for instance, in this case, if theta is equal to what is it? If I measure, for instance, with the x state pi over 2, okay, the average of sigma z is 0. Okay, because half go down and half go up. Okay, so the average are understandable, but the individual measurements are very strange. Okay, and in fact, here you notice that if I measure the spin in a state that is filtered as plus 1/2 n, the expected value, so let me just write it in this way. This is the spin operator. I measure on a state that has been filtered along n, it's equal to n over 2. Okay? It's just in the direction of the filter. The expected value. So the expected value of the spin is understandable, but each individual measurement is strange with certain probability. Okay. Yes. Is it clear? You have to practice, huh? It's a simple thing. I mean, most of the things that we will do about measurement will be on spin. So practice a little bit with filtering scalar products of this kind. Okay, so this is just the technology to calculate expectation value of spin. Okay. Now we have to do our hydrogen atom problem. So we will not be able, obviously, to finish this important piece of our story, but at least let me start. Okay. Okay. So the problem I would like to solve is the problem of two particles. One is the nucleus. Okay. It has a proton, for instance, and then there is an electron. Okay. They attract each other with a potential. So if I had to write a Hamiltonian for this system, first of all, I would need to involve two particles and therefore two momenta. So let me call it P1, say the momentum of the proton, square divided by twice the mass of the nucleus, plus the kinetic energy of the electron, okay, P2 squared divided by 2, the mass of the electron. I would call this 1 and this 2, or simplifying the thing, minus E squared divided by x2 minus x1, okay? The Coulomb potential between the two things. I could even generalize this object. I could imagine that this is a nucleus which has a certain number of protons and neutrons, okay? With a certain charge, Z, okay? Z is the nuclear charge. But the important thing is that there is only one electron. So for instance, this could be lithium, helium, which has 2 protons and 2 neutrons, by the way, okay? But ionized. So helium plus would be still described by this thing, because it has only one electron, okay? Lithium 2 plus, okay, has an even fatter nucleus, but still I have taken away 2 of the 3 electrons and only 1 is remaining, okay? So in some sense, I'm studying hydrogen-like problem with 1 electron and a nucleus, which might have a charge generally larger than 1. Okay, so if you want, you can put here a factor Z. Okay, so here you see that I have 2 systems, X1 and P1, and X2 and P2. For each 2 of them, I can write canonical commutational relationship, but I'm working essentially in a space that is 6-dimensional for the position. Okay, so writing wave function for this system seems to be like a very, very hard thing to do, right? I'm working in 6-dimensional space. Now, as you know from classical physics, the 2-body problem is in fact simpler than just working with 2 particles. I can reduce myself to a relative motion because there is a quantity that is conserved, okay, which is the center of mass motion, okay? These are only internal forces, so the center of mass. So you remember probably that the center of mass coordinate, okay, is equal to the weighted average, okay, of the 2 positions, weighted by the total mass. Okay? Now, you know that there is also another important object, which is the total momentum, which is the sum of the 2. Okay? So these 2 objects, center of mass and total momentum, are in fact canonically conjugate pairs. Okay? So you can verify, let me just do it for one of the components, say the X and the P X. Okay? The commutator is M1 and X1 plus M2 X2 divided by M, and I have to commute with P1 plus P2, meaning the X part. Okay? Then I have this commutator with this is IH bar. This commutator with this is IH bar. Okay? So what I have is M1 over M times IH bar plus M2 over M times IH bar. But M1 plus M2 is equal to M, right? And total mass. Okay, so you see that this is indeed IH. Okay, so it looks like center of mass and total momentum indeed seems to be conjugated there. Now, there is a second variable that I would like to invoke, which is the relative coordinate. So see x2 minus x1. Okay, so it's this coordinate here. If this is there is an origin x1 and this is x2. X2 minus x1 is the arrow that I'm drawing here. Okay, x2 minus x1. Okay, it's the relative coordinate, so it's the position of 2 as seen from 1. Is it clear? Now, this seems to be the natural thing to solve the two-body problem, right? A relative coordinate. After all, the interaction involves only the relative coordinate, and not the absolute position of the two. Okay, but the point is, what is the relative momentum in some sense? Okay, because I would like now to separate variables between center of mass and relative motion, right? I would like to do this clear separation of the two objects. And unfortunately, the first answer that comes to mind is wrong. So if I think of the relative momentum P as P2 minus P1, okay? It seems a reasonable thing. I mean, after all, the momentum of the particle 2 seen from the particle 1, you might think, maybe. No, this is not a relative velocity, okay? It's a relative momentum. So the actual interesting property that you should have is that it is canonically conjugate to this. And it's very simple to show that this commutator with that is not IH bar, okay? Simple. Look, X commutator with P, okay? This is X2 minus X1 commutator with, say, P2, I mean X component, minus P1 X component. Okay, so this commutator with that is IH bar. This commutator with that is IH bar plus. Okay, so the result is 2 IH bar. Not very nice. So this is not a good way of writing a relative momentum, although it looks very reasonable. Yeah. What? No, I have a minus.
Below the R.
Yeah.
The line below the R.
Ah, this is the total momentum, capital P. And this is small p, sorry. Okay? In the notes it's clear. But this is the total momentum. Let's call it P top. Okay? Canonically conjugate to the center of mass, which I indicate by big R. And this is the relative momentum, which is small p. And the answer is that small p is not P2 minus P1. You can verify that small p, the correct small p, is M1 over M times P2 minus M2 over M times P1. Okay? Now, if you insert these factors here and you do the same commutator, you will realize that things are fixed. Obviously, you might say, how do I discover? Just put two constants there and try to impose that you have that the commutator is 1, and you will realize, and also that this this object commutes with R. Okay, so I want to impose that the commutator of, say, X MP, any component, say, is equal to IH bar delta IJ. Okay, and I also want to impose that big R and small p commute. Okay, and if you do this, you will realize that, for instance, here the commutator of this with that gets minus M1 times M2 over M squared, and the commutator of this with that gets plus M1 times M2 over M squared. Okay, so the actual commutator is 0. Well, this commutator is fixed by essentially these two factors here. So I have here a factor M1 over M, and here I have a factor M2 over m. Okay, so when I do the actual calculation, I will get not IH bar for both, but I will get IH bar times m1 over m from this term. And from this, I will get plus IH bar m2 over m. Okay? And the sum of this thing is just IH. Okay?
What if I write P equal to M2 over M2 minus M1 over
You exchange these two things? It's wrong. Try to verify. You get it wrong.
Can you calculate it? Because I calculated when I got the same.
Ah, I see. Okay. Obviously, any two factors such that their sum is 1. Yes. But I try to impose the second. Okay? Good. Okay, let's do it. You put 2 here.
No, just what
You put here, you put 2 and 1. Okay? So I agree with you. You put here 2 and here 1, and the sum is the same. Okay? But now let's do this. Okay? So I have the commutator of, say, R and P, small p that I should do. Okay? So it's M1 over M times X1 plus M2 over M times X2. Let's suppose that I have only the X component, okay? Commutator with, where is it? M2 over M times P2, the X component, minus M1 over M, the 1 component, X component. Okay, so I do this with that, and this with that. And the answer is M2 squared divided by M squared IH bar minus M1 squared divided by M squared times IH bar. And this object is not 0. Yes. If you do exchange these two things, you get 1 and 2. The first one doesn't care, but this now becomes M2 times M1 minus M1 times M2. Okay, and the result is 0. So the correct thing is actually only one of the two. Although superficially it might look that it's irrelevant.
So,
Yeah.
in relative coordinate, the commutation of coordinate, in canonical coordinate, the commutation of the coordinate and the momentum is 0, while in relative it's not 0.
Repeat again.
So in relative coordinate you get like I h bar delta ij, while in canonical coordinate you get 0 for the commutation. By definition, is that
I did not understand your question.
no? I'm just asking whether you define such that in the canonical coordinate that you define big R and big P, their commutation becomes 0, and while in the relative coordinate it's still like IH delta, IH delta.
This commutator is not 0. This with that is IH bar.
Then what about the
This is the small p. So somehow the small p is a relative momentum, commutes with the total central mass coordinate. And obviously, I mean, in other words, R and big total T are one thing that totally commutes with X and small p. Okay? These two words commute among each other. This with that is canonical conjugate, IH bar the commutator. This with that, IH bar the commutator. But this commutes with that. Okay? Good. Is it clear? Now, you might be a bit worried by this very strange outcome, but I ask you to verify that this is indeed the only way where you can write. Remember, this Hamiltonian was the sum of the two kinetic energies, okay? And you can verify that this is equal to total momentum squared divided by twice the total mass, which is the center of mass kinetic energy, plus this relative momentum squared divided by the reduced mass, okay? Minus z squared over x. Okay? So the reduced mass is a very strange object. 1 over the reduced mass is equal to 1 over m1 plus 1 over m2. Okay? So you can prove that indeed with this definition, the sum of these two factors, two kinetic factors, nicely splits into a kinetic energy, which is the center of mass kinetic energy, and the relative motion kinetic energy, where the relative motion is governed, however, by a reduced mass. Okay. In this perspective, this is classical. I mean, in some sense, you have already done in the Kepler problem. Okay. The mass of the Earth and Sun, okay, that we insert in the Kepler problem is the reduced mass. Although, if the mass M2 or M1, which is say the mass of the Sun, okay, is enormously larger than the other mass, then you can do a first approximation, ignore, and say that the reduced mass is roughly equal to the mass of the light object. Okay, so for Earth and Sun, certainly it's a good approximation, but also for a proton and an electron, because the mass of the proton is 1,800 times bigger than the one of the proton. Okay, so certainly to a very good approximation, the reduced mass is essentially equal to the mass of the electron. Okay, is it clear? Now that I wrote the Hamiltonian in this way, okay, this suggests that I have split my six-dimensional problem into a center of mass and relative motion problem. And the center of mass is simple because there is no potential energy in which R is involved, right? The center of mass can be anywhere in space. It's pure free kinetic energy. Okay? So if I ask you to write the wave function of the full system, the wave function would be a function of R and the function of the relative coordinate. You realize that since these two objects, the center of mass and the relative motion, do not talk to each other, you can do the trick of separation of variables and tell me that this is equal to a function of R times a function of the relative position, right? The product of the two. Can you tell me what is the correct function of R if I have a system like this? Free particle for the center of mass. What is the free particle wave function? E to the I. Okay, so this is just a free plane wave, okay, for the center of mass. And the corresponding contribution to the total energy is h bar a squared over twice the mass. Okay, so with this separation of variables, essentially you can totally forget about the center of mass. It does a very simple motion. Okay, in absence of any potential confining the whole system. It has a free motion, okay, and you can just ignore. And in the remaining part of the story, we will concentrate on the relative motion wave function governed by this Hamiltonian. Is it clear? Okay, so from now on, we'll simply totally ignore R, and we would like to solve a problem that is slightly simpler. The problem is the following. I would like to find eigenfunctions of p squared over 2 mu minus z p squared over x times psi of x equal to p psi of x. Okay, so I'm doing a Schrödinger equation for the relative motion, so a particle in 3 dimensions with kinetic energy, an attractive Coulomb potential, and then I have to find the eigenvalues and the eigenfunctions. Okay, so I've reduced from 6-dimensional to 3-dimensional. Still, this 3-dimensional problem is complicated, but luckily enough, the potential, okay, depends only on the distance from the origin. Okay, so the potential doesn't depend on the angle. It is what you call a central potential. Okay, central potential is any V which depends only on the distance R from the origin. Okay, in this case it's -1 over R, but any potential that depends only on the distance is a central potential. You might have whatever. Okay. Now you remember from the Kepler problem what is the crucial thing that allows to solve this reduced relative motion. There is one of the law of Kepler that in particular tells you something about orbits, the classical orbits of this potential. The second law tells yeah, it's an area, it's the law of areas, but in particular it tells you that the motion occurs on a plane, right? Yes. So, and the area law, it's a statement of conservation of angular momentum. Okay, so if you think of this plane to be the say the x and y plane, this tells me that Lz only is involved. So the angular momentum along z, and the angular momentum along z is conserved, and therefore if you are farther away, you go slower. If you are closer, you have to go faster in such a way that you sweep equal areas, okay? Because the angular momentum is constant along the curve. Okay, so precisely this is the key to solving this central potential problem and reducing it to a radial problem, because you use the fact that this Hamiltonian commutes with the orbital angular momentum, okay? So the fact that the Hamiltonian commutes with the orbital angular momentum would allow you to write, rather than functions of x, functions of r, theta, and phi. And remember that theta and phi are the only variables that occur in the angular momentum. Okay? And surprisingly or not surprisingly, the functions that will be involved are the spherical harmonics. Okay? So this will come next time. So next time we'll see how to involve the spherical harmonics and the orbital momentum to further reduce the problem from 3-dimensional to 1-dimensional. Okay? And then you can solve it thanks to the fact that the potential is 1 over r. Okay? The first reduction from 3 to 1 dimension is true for any central potential. Okay? I'm just using the fact that the potential depends only on the distance. The second part, which is the exact solution, occurs only if you have a potential 1 over r. Okay, so I would not be able to solve the resulting one-dimensional problem for the radial coordinate exactly, I would need to do it numerically in general. But if the problem is 1 over r, I can do it analytically. Okay? Next time. Okay.